In this session, we are going to cover the Poisson random variable and another related random variable, which is called the exponential random variable. Okay. And it's actually derived from the binomial random variable with the assumption that the expectation n times p will be very small. Okay, so let's give an example. Supposing that you're going to toss a coin, capital N times. Coin is not necessarily fair, so we have a more general situation. And let's say that the probability of an H is P, okay? And the random variable we are interested in is the total number of H's after N tosses of the coin. You can imagine other situations in which you have, say, a success or a failure with or on and off, red or blue, and you have two possible results for each trial, and you have a capital N trials. And the probability of the thing that you're observing for is small. The expectation is small. Capital N times P is small. Okay, so what's the exact distribution? So the distribution that we want in such a case, which exactly describes the situation, is the binomial distribution. So the probability that x equals small n is equal to, for any sequence of heads and tails, it would be p to the n 1 minus p to the capital N minus n, right? And now how many of those are there? Well, there would be n factorial if you had capital N symbols that were distinct, but small n of them were h's, were all h's. So divide by small n factorial. And capital N minus small n of them were t's. So you divide by, again, by capital N minus small n factorial. And that's just the PMF for the binomial random variable. Okay. Now, supposing that p is small enough that n times p, the expectation, is very small. Okay. And we have so very large n, then we can start making approximations to this. All right. Now, what I would like you to do is to go through the notes. We make use of the Taylor expansion for 1 minus p to the n minus n, log of 1 minus p, and so on. And we make use of Stirling's approximation. And you should go through this once in your life. And what you will get is that the probability that x is equal to n is approximately equal to 1 over small n factorial np to the n e to the minus np. So here's this np that I was talking about. That was the expectation for the binomial random variable. And typically we will write that as, in this course, we will write that as lambda, right? We use lambda is equal to np, and then finally we get this. The probability that x is equal to small n can take values 0, 1, 2, 3, and so on up to any integer. That's approximately equal to lambda to the n divided by n factorial e to the negative lambda, and that is the Poisson random variable. So this is used for rare events when and you might have when you can approximate the binomial distribution, the binomial EMF by this PM. Okay, so let's do some examples. So we're going to spend from 12 noon to 1 p.m. at lec09. We're going to see how many cars are entering the traffic circle. We know that on average, a car enters the traffic circle every 5 seconds. So our lambda is 1 car per 5-second interval. Okay. What's the probability that no car enters in a 5-second interval? Okay, so we go back here. Remember, the probability that x is equal to 0 is approximately lambda to the 0 over 0 factorial e to the negative lambda. And lambda is 1 car for every 5-second interval. Okay. So the probability that x equals 0 because lambda to the 0 over 0 factorial e to the negative lambda equals e to the negative lambda. And in this case, lambda was 1 car for every 5-second interval. Okay. Supposing that it was 1 car, and supposing that our data said that 1 car enters in a 10-second interval on average. Okay. So okay, we want the probability that 1 car enters. Sorry, okay, I messed up there. Keeping the same lambda, 1 car every 5 seconds on average. What's the probability that 1 car enters in a 10-second interval? Okay, the probability is x is equal to 1. X is equal to n equals lambda to the n over n factorial e to the negative lambda n. So the probability that x is equal to 1 car in a 10-second interval is, now you can, we have to make sure that we're talking about the same thing, right? So 1 car on average in a 5-second interval means 2 cars on average in a 10-second interval. So here our lambda is 2. So that's 2 to the 1 over, we expect, we're looking for 1 car entering, 1 factorial, e to the negative lambda. Lambda is equal to 2. That's equal to 2 times the exponential of minus 2. Okay. Okay. Next question. So let's suppose that there are, at LUMS, there are on average 1 serious biking accident every 2 weeks. What is the probability of more than 2 accidents in a given week? Okay. Again, let's make sure that we have our units straight when we do this problem. Okay, so what? We work out the expectation, which is lambda. If we expect 1 accident every 2 weeks, then we expect 0.5 accidents in a week. Okay. So the lambda that we use is lambda equals 0.5. So now, then if in general the probability that x equals n is equal to lambda to the n over n factorial e to the minus lambda. And then the probability that x is equal to n when lambda is equal to lambda equals 0.5 is 0.5 to the n over n factorial e to the negative lambda is 0.5. Now, what's the probability of more than 2 accidents in a given week? That's 1 minus the probability of 0 accidents minus the probability of 1 accident. Okay, so 1 minus the probability that x equals 0 minus the probability that x equals 1 minus the probability that x equals 2, right? We were asked for more than 2 accidents, so we also have to subtract off the probability that x is equal to 2. So you put these in here, n equals 0, n equals 1, and n equals 2, and you should be able to work out the answer. Okay. An exercise for you to do. There are on average 3 traffic accidents on a given road each month. What's the probability of 5 accidents in a month? What's the probability of less than 3 accidents in a month? So that's the probability of 0 plus the probability of 1 plus the probability of 2. What's the probability of at least 2 accidents? That's 1 minus the probability of 0 minus the probability of 1. And here your lambda is going to be equal to 3 if you're doing everything per month. Okay. A little bit more about the Poisson random variable. X is the number of outcomes of an event during a time interval or in a specified region. Okay. So the number of emails received in an hour, the number of power failures in a week. Hopefully these are rare events. The number of wolves in a given 1,000 hectares of forest. Right? You won't find that. Right? And the original example, the Prussian army needed to set aside money for widows' pensions, and Poisson worked on the problem of the number of Prussian cavalry officers kicked to death in a year, and therefore the widows' pension, by their horses. Hopefully that doesn't happen very often. Some assumptions: the number of outcomes in an interval or in a region is independent of the number of outcomes in another disjoint interval or region. Okay, so number of people who enter a McDonald's outlet in 10 minutes at the beginning of the hour as opposed to the end of the hour, hopefully. So you would assume that these are independent. The number of wolves found in 1,000 hectares here and then an adjoining 1,000 hectares there should be independent of each other. Okay, we're assuming that the probability that a single event will occur during a short interval or in a small region is proportional to the length of the interval, the size of the region, and it doesn't depend upon the number of outcomes outside of the region. And the probability that more than one outcome in a small enough time or in a small enough region is negligible. Okay, so the PMF for a Poisson random variable x is of the form e to the negative lambda to the x over x factorial. X takes values 0, 1, 2, and so on. Lambda is the expectation. So x equals lambda. The variance is also equal to lambda. And we saw that it can be derived from binomial random variable. Okay. Now we come to the exponential random variable. So the number of events in an interval is discrete, right? Car entered the traffic circle. Car entered the traffic circle, or didn't. 3 cars or 2 cars or 0 cars enter the traffic circle in a given period of time. So those are discrete. On the other hand, the times between the occurrence of Poisson events, those times are continuous, right? And in principle, it could go, the time between emails could go from 0 seconds to infinitely many seconds. So the Poisson distribution is concerned with the number of events that occur in a given interval or region. The exponential distribution is concerned with the time interval between events that we believe are Poisson distributed. So these two, the Poisson random variable and the exponential random variable, are related in this way. So let's say that power failures occur once every 2 hours. Okay. So there's your average, there's your lambda. We can use the Poisson distribution to estimate the probability of 2 failures in the next hour. The exponential distribution would be used to estimate the probability that the time between 2 failures will be between 10 minutes and 25 minutes. Remember to keep your units straight. If you're going to give your lambda in terms of occurrences per hour, then your time should be measured in hours also, right? So you would convert minutes to hours. Okay, so once again, if you have expected a certain number of Poisson events per interval, lambda, then the Poisson distribution is the probability that x equals n equals lambda to the n over n factorial e to the negative lambda. So this lambda, this expectation, is a parameter in the Poisson distribution. And that's discrete. So that's x. The interval y between events. So if this is events per hour, then y will be hours between Poisson events occurring. So the interval y between events will be a non-negative real number, right? And because the Poisson events are random, the time between Poisson distributed events is also a random variable. Okay, and this is what it works out to be. If your if in the Poisson distribution you had the parameter lambda, which is both the expectation and the variance, then this lambda will also occur in the exponential distribution, which describes the time between events. And then in this PDF, f sub y of y, that will be lambda e to the negative lambda y for y greater than 0. And it'll be 0 otherwise. Yeah, you don't have minus 3 seconds between power failures. Okay. Another way of looking at it is that we write lambda as 1 over beta, or beta is equal to 1 over lambda. And in that case, the distribution is, the PDF is given as 1 over beta e to the negative y over beta for y greater than 0, and it's equal to 0 otherwise. Okay, and then for the exponential random variable, the expectation is beta, and the variance is beta squared. Okay, so let's do an example. Power failures occur at an average rate of 2 per hour. What's the probability of less than an hour interval between 2 power failures? So what's the probability that a power failure occurs between now, time is equal to 0, to time is equal to 1 hour? Okay, so the average rate is lambda is equal to 2 per hour. So your beta, which is equal to 1 over lambda, is 1 over 2, is equal to 0.5 hours between power failures. So the probability of an interval of length 1 to 1 hour between power failures is, remember, for PDFs, you're going to integrate. So you integrate from between y equals 0, the time is 0 hours, to y equals 1 hour, 1 over beta, which is lambda, right? E to the negative y over beta, beta is 0.5 dy. And if I do that calculation, I get 1 minus e to the minus 2, 1 minus the exponential minus 2. What's the probability of a time between failures of more than 1 hour? Well, that would be 1 minus that. So it would be the exponential of minus 2. Okay, here's an example. Another one. Okay, so the failure of a certain type of electronic component is a Poisson process. Suppose that a particular model on average lasts for beta is equal to 5 years. What's the probability that a given component will last longer than t equals 8 years? So here you're going to integrate the PDF for the exponential random variable from t equals 8 to t equals infinity. So 1 over beta, 1 over 5, times integrate from t equals 8 to t equals infinity, right? Greater than 8. 1 over beta, e to the minus t over beta was minus t over beta, and beta was 5 dt, and that will work out to about 0.2 if you do the integration. Okay. Okay, so when I have a random variable, I would like to know its PDF. We've discussed that. I would also like to know its CDF. That can be convenient for me. So what is the CDF? So if the exponential random variable is thought of as the time between 2 Poisson distributed events, the CDF will be the probability that time will be less than some number. So once again, the PDF for the exponential random variable y was equal to 0 if y was less than 0, and it was equal to lambda e to the negative lambda y. y was greater than or equal to 0. Lambda is, we're also writing that as lambda equals 1 over beta. So the cumulative distribution up to t, right, is equal to y goes from minus infinity to t f of y dy. Now that's the CDF by definition. Now you don't need to integrate over an interval where everything is 0. So we're going to integrate from y equals 0 to y equals t, lambda e to the negative lambda y dy, and that will be equal to 1 minus e to the negative lambda t, or since lambda is equal to 1 over beta, 1 minus e to the negative t over beta. The probability then, this is the probability that the time between two Poisson events, Poisson distributed events, is less than or equal to t. So the probability that the time between two Poisson events is greater than or equal to t is 1 minus this, which will be equal to e to the negative lambda t, which is also equal to e to the minus t over beta, since beta is equal to 1 over lambda. Okay, supposing that we observe that power failures happen every 10 hours. And we just had a power failure. What's the probability the next power failure will be in more than 15 hours? Well, we use this result. The probability that time will be greater than or equal to t is equal to 15 hours is e to the minus, the time we're looking for is 15, over beta is the average of 10 hours between power failures. So the exponential minus 1.5. Okay, now here's a very interesting property of the exponential random variable. And no other random variable has this property. Okay. Supposing a bus comes every 10 minutes. Okay, we're waiting for the bus. We've waited 8 minutes. So intuitively, if I've waited a long time, then that bus should be coming along very soon. So what would be the expected time that I have to wait? Okay. All right, so we're going to do this carefully. On average, the waiting time is 10 minutes. The exponentially distributed waiting time for the Poisson distributed bus arrivals is 10 minutes. So beta is your 10 minutes. We've waited a time t equals 8 minutes. What's the probability that the bus will come in the next 4 minutes? Okay. Okay, so lambda is 0.1 bus arrivals per minute. So the probability that the time will be less than my 8 minutes per 4 minutes, given that I've already waited, that the time is guaranteed to be bigger than 8 minutes. Since I waited 8 minutes, the time will be bigger than 8 minutes. That's the probability. Oh, well, that's a conditional probability, right? So that's the probability that the time will be less than or equal to 8 plus 4 minutes, 12 minutes, and that the probability will be greater than 8 minutes, divided by the probability that the time will be greater than 8 minutes. Okay. Well, if I know that the time is less than or equal to 12 minutes, and I know that the time is bigger than 8 minutes, that means that the time lies between 8 and 12 minutes. Okay. Divided by the probability that the time is bigger than 8 minutes. Okay. Now, how can I find this? Well, I can take the cumulative distribution up to 12 minutes, and I can subtract the cumulative distribution up to 8 minutes, divided by, well, I can take the cumulative distribution up to 8 minutes, and I can take 1 minus that, right? And what was the cumulative distribution? The cumulative distribution was given by this thing here, 1 minus e to the negative 1. Okay, so this here is 1 minus exponential of negative lambda was 0.1, t was 12 minutes, minus 1 minus the exponential of negative lambda was 0.1 times 8, divided by 1 minus that, so divided by 1 minus this thing, which will be exponential of minus 0.1 times 8. So if I do that, I get 1 minus the exponential of minus 0.1 times 4. But then I recognize that this is in fact the same as this. This is in fact the same as that. Okay, so this is the important thing to note here. The probability that you will have to wait total less than 4 more minutes, given that you've waited 8 minutes, is the same as the probability that you will have to wait less than 4 minutes. Okay. So the exponential random variable has forgotten that you've waited 8 minutes. Okay. Once again, the probability that the bus will come in the next 4 minutes has not been affected in any way by the fact that you have already been waiting 8 minutes. Okay. This is called the memoryless property. And this is a unique property of the exponential PDF. So, supposing that events are Poisson distributed with an arrival rate lambda, and you want the probability that the total time that you will have to wait is less than or equal to y, x plus y, given that you've already waited x. So given that it's guaranteed to be bigger than x. If you do the calculations using the definition of conditional probability, then you can write that in terms of the total probabilities of the cumulative distributions. And then when you sort that out, this is just going to be equal to CDF of y, which is a probability that y will be less than or equal to small y. Okay. So once again, that's the memoryless property. The fact that you've waited an hour for the bus that should have come in 10 minutes doesn't matter. Your expected waiting time does not change. Okay. So once again, the unique property of the exponential random variable.